the lecture of Fresnel's biprism, what we did was we studied the construction of the Fresnel biprism experiment, and we found how two virtual sources S1 and S2 sources, they are formed when the light it gets refracted from the Fresnel's biprism, and we did that the Fresnel biprism it is made up of two prisms which are cemented base to base, and the angle of such prisms is very small and it is represented by alpha, and this alpha is about 30 minutes, and 30 minutes is half a degree, which is a very small angle. So we did the construction of Fresnel biprism and we found how two virtual sources are formed, since these are the sources which are formed from the same source, and hence S1 and S2 they will be coherent sources. So coherent sources will be formed, and hence the interference pattern that is obtained is stationary interference pattern. So we also found we also did how to measure small d. Small d is the distance between the virtual sources S1 and S2. So we found the value of the expression of small d using the displacement method. So in that method we took a convex lens, and changing the position of convex lens, we found two images which were at a distance of d1 and d2, and we calculated how small d can be found using d1 and d2. So that was the displacement method. Next method of finding small d is the deviation method. Here we use the angle of deviation of the prism. We use the concept of angle of deviation of the prism. First of all, we will look at the concept of angle of deviation. So here is shown a prism of angle of prism is alpha. Alpha is the refracting angle of the prism, and an incident beam it falls on the prism and it gets refracted and then it gets transmitted. So the angle which is made between the incident, now incident ray it is extended in forward direction, and the transmitted ray it is extended in the backward direction. So the angle which is made between the incident and the transmitted ray, that is represented by delta, and this angle is called as angle of deviation. So there is always a minimum angle of deviation for a particular prism, that is delta m, which is represented by delta m. This is the angle of minimum deviation, and this delta m it can be found using alpha and mu of the prism. Mu is the refractive index of the material of the prism. Using alpha, that is if we know alpha, the refracting angle of the prism, and we know mu, then we can easily find the angle of minimum deviation, and the formula is given by this expression, that is mu it is equal to sine of delta m plus alpha divided by 2 divided by sine of alpha divided by 2. So this derivation is not in the syllabus. What you have to do is to write directly this expression, and then we will derive how small d can be found using the deviation method. So the derivation of this expression you have already done in your plus 1 plus 2 class. So the derivation is not in your syllabus. The derivation of finding small d after this expression that you must do, that is in your syllabus, and a numerical on this article it has been asked in the question paper of 2018 or 2019. So this method is not given in your Moderns book, and this method is important from the exam point of view. So how we use this particular expression, or how we use the concept of angle of deviation to find small d, which is the distance between the two virtual sources. So here we have seen that the angle of deviation is the angle which is made between incident ray and the transmitted ray. So in the case of Fresnel biprism, there we drew light rays from the source capital S on the Fresnel biprism, and the rays which were falling on the Fresnel biprism, they got refracted and they were falling on the screen. So the angle which is made by the incident, this is the incident ray and this is the transmitted ray, the ray which is transmitted after the refraction from the biprism. So the angle which is made is this angle, the transmitted ray, it is extended in the backward direction, and here is the source, virtual source, which is virtual source that comes up is the S1 source, and the light ray which gets refracted from the lower face of the biprism, it gets refracted and then it transmits and it falls on the screen, and when this light ray is extended in backward direction, we get a S2 source, which is S1 and S2, these are the virtual sources. So incident ray and the transmitted ray, when the transmitted ray, this particular ray is extended in backward direction, so the angle which is made between the incident and the light ray which is extended in backward direction, this will be delta, which is the angle of deviation. So we will use the concept of angle of deviation. Now the length S1s, the total length between S1 and S2 is small d, so the length S1s will be d by 2. So here is a figure that is shown. This triangle will be almost a right angle triangle. This triangle will be almost a right angle triangle where 90 degree or the right angle will be formed at the source capital S. So the distance S1s will be equal to d by 2, and the distance of the source from the Fresnel biprism is equal to small a. That is, this is the source S and this will be the center of the biprism. So this distance is equal to small a, and the angle, this particular angle is the angle of deviation. So in this case, the Fresnel biprism, it is a very thin prism. As we know, the angle that is made over here, this is about 179 degree. So this biprism will be very thin. So in the view of the prism very thin, that is for the case when the prism is very thin, delta m, that is the angle of minimum deviation, and the refractive angle of the prism, that is the angle of the prism alpha, they are quite small. So we are using approximation for the case of thin prism. So for the case of thin prism, delta m and alpha, they will be very, very small. Therefore, sine of a small angle, sine of theta, so theta is very, very small. So sine theta, it can be approximated to simply theta. So this is for theta, which is very small. Now in this particular formula, we have sine of delta m plus alpha divided by 2. So we know for thin prism, delta m is also very small and alpha is also very small. So here we have divided by 2. So this whole angle inside the sine function, this whole angle will be very small, and hence sine of this angle, it can be approximated to simply this particular angle. Similar is the case in the denominator, that is sine of alpha by 2, it can be approximated to simply alpha by 2. So mu will be approximately equal to, for the case of thin prism, it will be approximated to delta m plus alpha divided by 2 divided by alpha by 2. So this can be simply equated to delta m plus alpha divided by alpha. So next approximation that we will use is same for thin prism. So we will drop the subscript small m, that is in this particular term delta m, we will drop this, we will not write this subscript small m. This is because the thin prism, they work or they function at or minimum or near minimum deviation. They function at or they work near minimum deviation. So this is the reason we will write delta m to simply delta, that is the angle of deviation for all the incident rays, for all the incident angles, it will almost be the same. The angle of deviation, it varies with the incident angle. So this concept we have done in our +2 class, that the angle of deviation, it varies with incident angle. But in case of a very thin prism, the angle of deviation is approximately, all the angle of deviations, they can be approximated to delta m, because delta m is already very small and angle of deviation delta will also be very small for the thin prism. So the minimum angle of deviation, it can be approximated to delta, or you can say delta, it can be approximated to the angle of minimum deviation. So instead of delta m, we can simply write delta, because the thin prisms, they work at or near minimum deviation. So in this case delta m can be simply written to as delta. So when you simplify this expression, you will get this first equation, which is mu minus 1 times alpha. It will be simply equal to delta. So this is the first equation. Now in this particular triangle, we have d by 2, which is equal to s1. S1 as length is equal to d by 2, and this is the angle of deviation delta. Now we know for the case of thin prisms, delta is also very small, and hence d by 2, this will also be very small length. So we will use the concept in the circle that we use in the case of circle. That is, if we have a circle and there is a arc of length small l, and the radius of the circle is, let's say, that is small r, and this is the angle which is made by the arc at the center of the circle. Let's say that angle is theta. So in that case, theta, it can be equated to small l by r. So this is the formula that we will use in this particular triangle. That is, d by 2 is very small, and hence this can be approximated to the arc of a circle whose radius is small a. So delta will be approximately equal to the length of the arc, which is, here we have length of the arc divided by radius. So we will divide the length of the arc is equal to d by 2. We will divide this by small a. So this is the second approximation that we are using. So this was the first approximation, that we are using a thin prism, and hence delta m and alpha, these are very small, and also for the case of thin prism, they function at minimum deviation. So delta m can be equated to simply delta. So this is the next approximation, that d by 2 is also very small, and hence we can write delta can be approximated to d by 2 divided by small a, and from here delta will be approximately equal to d by 2a. So we have first equation, we have delta is equal to mu minus 1 times alpha, and over here we have delta is equal to d by 2a. So we can equate these two equations. So we will get mu minus 1 times alpha will be equal to d by 2a. Simply we will equate first and second equation. So from here we can calculate the value of small d, which will be equal to 2 times mu minus 1 alpha times a, where mu is the refractive index of the material of the prism, alpha is the refracting angle, or you can simply say it is the angle of the prism, and alpha is this angle. This particular angle is the angle of the prism times a. A is the distance of the source from the Fresnel's biprism. So in the question, in the numerical, it will be given to you alpha, then mu refractive index of the prism, and also small a, which is the distance of the source from the Fresnel biprism, and you can easily calculate the value of small d.